So let me first thank the organizer, Mauro and Wilson, for the invitation to this very, very nice workshop, and also for the organization. So I'm going to show you our latest measurements and analysis of vortex core spectroscopy on YBCO, which led us to the conclusion that the vortex cores in YBCO were really BCS D-wave. This work was done in University of Geneva, a group of Christoph Renner. Most of the measurements have been done by Jens Brewer for his PhD thesis, and the calculation by Christophe Berthaud, which is here in the workshop. So I don't think there is really need to stress how complex is getting the phase diagram for the cuprate. This is YBCO, and except the superconducting dome, you might know that there are more and more lines added to this diagram, separated phases which are not completely understood. So there are very strong correlation in these systems. And this is probably the reason why the spectroscopy, tunneling spectroscopy in the cuprates are actually providing spectra which are not the BCS one expected for a D-wave superconductor. You have here niobium superconductor, where the tunneling spectra is really textbook S-wave superconductor, BCS. But you see here bismuth 2212, 2201, YBCO or LASCO. The tunneling spectra are really different from what is expected for a pure D-wave superconductor. So in this talk, I will start by introducing the vortex core spectroscopy, which has actually been already discussed in previous talks, and show you this unexplained until now vortex core spectral signature in YBCO, and show you how we can model the maps we are performing by STM, and conclude that the vortex cores in the system is really D-wave signature. Okay, so rapidly scanning tunneling spectroscopy on vortices. You know, of course, vortex is a singularity in the order parameter, and what is expected is that when you acquire spectra outside or inside the vortex cores, they should be different, and you just exploit the difference in this in the conductance out and inside the vortices to make a map, a spectroscopic map of the vortices. This is clear. This is niobium diselenide, but what about spectroscopy signature of the core? So again, the order parameter, which is singular at the position of the vortex, and in a way it's a kind of potential well, where you have bound states, quasi-particle bound states, and the spacing actually, which was calculated by Carly in the 60s, is of the order of delta square over EF, which is a very small quantity. And actually, with the STM, this quantity is not the spacing between these states is not measurable, since the temperature is broadening all these effects. As a consequence, the vortex core center is usually revealing a zero bias anomaly, which is actually consisting of a set of bound states which are very closely spaced. And when you go from the center to the outside of the vortex, you get the splitting of this peak. Due to the fact that this angular momenta increase and the weight, spectral weight, is pushed towards higher energies. So this is the calculation. And of course, the first measurement in the 90s by Hess really showed the expected behavior for BCS S-wave vortex core. And this has been then been measured on a different variety of compounds, S-wave superconductors, dechalcogenides, iron selenide, or borocarbide compounds, where in all cases you see that the center of the core is showing a zero bias anomaly and a split while going from the inside to the outside. Okay, so far so good, but what about a D-wave superconductor? So vortices have been seen in a number of cases. This is YBCO and BISCO. You see the vortices are quite tiny, and actually you can compare the size of this of the cores with the ones of niobium diselenide, and due to the fact that coherence length is really small in the cuprates, the cores appear really small in the images. We have usually non-ordered vortices, so disordered lattices. And the spectroscopy, this is for YBCO, a trace taken from the outside to the inside of the core will show you that kind of evolution. So outside the vortex, we have the quite strong presence of coherence peaks, which are located at the position of the superconducting gap. But at the center of the core, you have this pair of peaks, which is located at 5 or 6 millivolts, and they don't disperse while crossing the vortex. So, okay, this was the measurement, and now the question is, what is the theory providing for the D-wave response of a vortex core? And this is the calculation, and you see that it's essentially similar to the S-wave situation, a zero bias anomaly and a dispersion, with the main difference that there are no bound states for a D-wave vortex, and it's not possible to attribute and to associate these finite energy states to bound states in a D-wave superconductor. Actually, we also measured subgap states in the center of the vortices for BISCO. So in all cases, we were not seeing zero bias anomaly for in the spectroscopy of cuprates. So there were a number of theories which were published in order to understand that kind of the presence of finite energy states in the center of the cores. But none of these theories were able to explain exactly what we were seeing. So we started new measurements, and the result is the following one. You see that from the outside to the inside of the cores, these subgap states are really located at the constant energy in position and in magnitude. So by performing a statistical analysis of the spectroscopic features, you can see that actually here the X scale of these diagrams is providing you the position compared to the center of the core, 1 being the center and the smaller number being the outside of the core. You see that when you enter the core, the zero bias conductance increases, the coherence peaks decrease, but the subgap state magnitude remain constant. So there is no correlation between the subgap states and the vortices. More, if you make a map at zero field, you see that this is the average spectrum of the whole map, also reveal the presence of subgap states. So we can really deduce that these subgap states have nothing to do with the fact that they are measured inside the core. So we had to consider a very simple model where we consider actually 2 parallel channels. The 2 channels are added in order to provide the measurement. So the one channel is the one which we call the incoherent channel, which is actually involving all these the subgap state feature and a number of other features from the spectra. The second channel is the purely superconducting channel, which actually can be calculated considering a bare band structure with realistic coefficients and D-wave pairing. And a weighted sum of these two channels will provide the measurement. And actually, our estimation gives a contribution of 15 to 20% only of the superconducting channel. So we have the situation where we have this incoherent channel, which is uniformly detected over the surface. And let's do the same, the following procedure. We take as a reference spectrum the spectrum measured outside the vortices, which is in our model consisting in the incoherent plus the superconducting D-wave part. Then the other spectra, like for example the one measured at the center of the core, will be the sum, the addition of the incoherent plus the D-wave core signature. And so, assuming that this incoherent channel is uniform all over the surface, a subtraction of these two will provide you the difference between the D-wave core spectrum minus the D-wave superconducting spectrum. So this is the measurement, but we need a model to compare this situation. So actually we apply this subtraction procedure, so take one reference spectrum to the whole map, and we now come to the model. Actually, I won't go into the details for this model, so since the next talk of Christophe Berthaud will focus on this topic. Just let me tell you that we need to measure the density of state, the local density of state, which requires the calculation of the green function. The green function requires the inversion of a matrix, which can be quite tough to calculate if you consider large-scale lattices. In this model, we use a lattice which consisted of about 1,000 by 1,000 units, which was large enough to include a number of vortices which was corresponding to the 5 Tesla field we were using in the measurements. So this is the procedure. We take our spectroscopic image, spectroscopic map of the vortices, which allows us to find the position of the vortices and set the position of the singularities. And then we generate a random distribution of flux line around this field of view, and then select specific traces from the measurement. And then from the model, we calculate the local DOS for each position of the field of view of the map, and minimize the error between the measurement and the calculation. So this is the actual measurement with the 4 different traces shown here, so after subtraction of the reference spectrum. And this is the calculation. And you see that the equivalence, although of course the details and the small wiggles you can see from spectrum to spectrum can change, but the overall evolution of all these spectra is consistent with the calculation. Okay, so you might say that it's clear that the first spectrum is almost flat to 0 since we subtracted itself in a sense. So the traces started here at the center, and we subtracted the same spectrum. So by construction, it had to be flat with a peak, maybe. So to prove that this is realistic, let's consider other traces. Like for example here, the traces 1 and 4, which are going along different crystallographic direction. And you see that compared to the traces 2 and 3, which are actually going along the 1-1 direction of the macroscopic lattice, traces 1 and 4, which are going oriented along the 1-0 direction, reveal a small bias anomaly at 0. And actually the model, the same model, with the same procedure and considering the same traces, 1 and 4, is also providing the small spectral weight at 0. So it really means that we see here that depending on the direction we consider, the decay of this zero bias anomaly is different. And this can actually be well illustrated in the case of a single vortex. So this is a single vortex, a self-consistent calculation of one vortex with the same macroscopic lattice as a background. And you see here two traces going from the center to the outside following the 1, 0 direction. And you see that the zero bias peak decays not completely. So you still have a zero bias anomaly at a certain distance. While along the other direction, you see that the decay is much more pronounced. And this is a fact which is quite important. And it's essentially due to the band structure of the material. So it's really, if you would do the same analysis with an S-wave vortex, essentially you would find the same evolution. So it's really a question of band structure of the material, and this dominates the spatial evolution of the spectra. Another point concerns the surrounding vortices. So I told you that we were generating random distribution of vortices. Actually, there were 600 distributions which were generated. And the minimization was necessary since, depending on the position of this random position vortices, the exact details of the spectra are changing. You can see here the three different configurations and the three different the four traces for each of these configurations. Look, for example, at the last column here. You see quite clear differences between these traces. You see here some kind of splits, some more pronounced splits, and a zero bias single value peak at the center. So it also means that the disorder of the vortices is really influences all the signature of all the cores. So in a sense, it's almost meaningless to talk about, in a case of a disordered vortex lattice, it's almost meaningless to talk about a specific signature of the core. It really depends on the environment. So the last remark is actually, we know now that these bound states, these subgap states, are not specific to the vortex cores. But we don't really know where they are coming from. We know they are uniformly spread over the surface. We measure them with a constant intensity. And it's quite tempting to link these states with the charge order, which has been discovered not so long time ago in the cuprates. This is the example of BISCO vortex cores, are clearly seen. And you see that in each of these cores, there is a modulation, a pattern, which is actually 4 by 4 unit cells. It's the same kind of modulation which is seen above TC in the pseudo-gap regime. And it was clearly established that the modulation which was seen in the vortex, in the spectroscopy in BISCO was the charge order which was discovered by X-ray techniques and in YBCO and also BISCO. Okay, so the link between this modulation and charge order was established. Now we also have a hint in the sense that this modulation, this is a zoom of a core in BISCO where you see this modulation. And actually this modulation is maximum precisely at the energy of these subgap states. So this subgap state seems to be completely linked with this modulation, which are also linked with the charge order. So it's quite tempting to associate this subgap state with this charge density wave, which are quite now routinely measured in your cuprates. With an important conclusion, if that happens to be true, we clearly see that crossing a vortex, having a field or not, is not affecting at all this signature of finite energy state, which would mean that this state, and possibly the charge density wave, is not affected, not competing and doing nothing special with superconductivity. They just coexist as we claim with this two parallel channel model. Okay. So let me conclude. First, the take-home message with the first thing is that these subgap states of finite energy states measured in YBCO are not specifically connected and linked with the vortex cores. We assume that they belong to a distinct incoherent channel, and probably as well as some other spectroscopic feature, actually, where that we include all these features in the same channel. Concerning the coherent channel, we see that it's fully BCS, D-wave. The contribution of this channel is of the order of 15% in the total current, which is quite weak. And this also explains why this zero bias anomaly in the cores is not emerging as they emerge in the case of S2F superconductors. And we see that by modeling this, the vortex distribution and comparing with the data, we can really extract this zero bias anomaly which is expected in the case of a D-wave superconductor. Now finally, we might link this subgap states with this the charge order, which would imply in that case that this charge order is not competing with superconductivity. These are the references you can read, which is actually a summary of all this talk. Thank you for your attention.
Thank you very much, Ivan. Are there questions? Yes.
I'm just looking at your data. It looked like there was a distinct difference between the BISCO data, where it looked like the as you scanned along 10 nanometers, it was nearly flat and very low